I'll do the first question, Josh will do the next one, and we'll alternate commenting on exam style. So we're not going to be trying to teach you stuff, we're going to be trying to show you how to apply the knowledge you have in an exam scenario. Okay. First question is my question. Josh, do you want to say hi to everybody?
So I'm still waiting to see, I don't see it on our screen just yet, but we should be streaming. So hi, I'm Josh, and I'll be helping Daniel.
Yeah.
Going over these questions. So Daniel's up first.
It's always tricky to know. Oh, we're up now. It's always tricky to know whether we're actually streaming or not. I don't know. Anyway, I'm first. Cool. Question 1. Find the value to be given to f of 2 that will make this object continuous at 2. Okay, so let us remind ourselves what the definition of continuity is. Just quickly, it means the the limit from the left is equal to the limit from the right, which is equal to the definition of the which is equal to the function value at that point. So maybe I'll just put that down to show the marker that I know what's going on. And yes, it's nice to show off that you know what the definition of continuity is, but this is also a really good idea because it gives you a kind of starting point from which you can start doing things. So this is the definition of continuous, and this is what we must do. It's like stating our objective. I will now perform the demonstration that f is continuous at 2. So this is what I'm going to do, and here it is. So the function is this one up here, so that's x minus 2, and the denominator, I'll just factorize that real quick, that's going to be x minus 2, x minus 1. And because I'm considering values of x which are strictly less than 2, I can just cancel these bits right off. This is equal to and then there's no trouble with saying what this might be. This is just 1. All right, and the other side. Again, this is going to be x minus 2 over the factorization. Which is again 1. Okay. Now, we don't actually know what f of 2 is. In fact, this function here, this one over here, the function is not defined at x equals 2. You have this division by 0 at x equals 2. So the function is not defined at x equals 2, but if we were to define it to be equal to 1, then the function would be continuous at that point. So if we define f of 2 to be 1, then the limit x behold, Josh.
Right. So, yeah, I mean, this is a nice answer. It's short and clear. I guess technically you could make your argument a little bit shorter, because I mean, this and this together, if they're both equal, then you're just talking about the limit as x approaches 2. So a slightly shorter way to state it is it's continuous. You'd say, actually, what I really would like to do is rub some parts
Go
out.
for it.
So I mean, f of x is continuous at x equal 2 if this is true, which actually is in some ways the same statement as what Daniel wrote down. So this is really saying that both left and right hand limit approach the same value. So you could save yourself maybe one line of writing just by only doing, in both the left and the right hand limit had the exact same property. We're never looking at x equals 2, so these two factors were just non-zero numbers cancelling out.
Yeah. With this limit at a point, there's a hole where x is 2, and the limit never actually looks at what happens at x equals 2, just around what x happens, just around x equals 2. So maybe I'll get rid of that one as well.
Yes. So if you had just written this, I think this is also an acceptable solution, and it takes a few less lines, but it wasn't that much shorter.
Yeah, your solution is better because it's shorter. I like it. I didn't completely take off my teacher hat, because taking the left-hand limit and the right-hand limit will work in more circumstances, but Josh's answer is better for this one, and it's probably what I should recommend you do in your exams, because you don't have a lot of time. So shorter is better in this case. Cool. Thank you, Josh.
Okay.
Your turn.
Right.
You seen the black? Oh, you've got
This one?
black. Yeah.
Okay, so this next question, we're given a function over, and so this is, we're given a function over this interval 0, 5, and we want to find all the critical points. Now, whether or not I would want you to write this down in a test, I think a short sentence here would probably help you as well, is just remind ourselves what the critical points. So the critical points of a continuous, I'm very lazy, I say CTS, function over a closed interval. Well, there's actually 3 types we'll need to search for. There's the endpoints. You don't really need to search for those as such. You are given them. Endpoints of the interval. The stationary points, those points, well, this is differentiable, it's the points with derivative 0. And one more point is points where the derivative is not defined. So I call this function, I should call it f, to make my life easy, where the f dx is not defined. Now that might be something nice to write down, because it does show you know what you're talking about. So here, well, we know the endpoints straight away. The endpoints here are x equals 0 and x equals 5. And it might be wise, this function, it might be wise to actually plot this just so we know visually where our critical points are. So that's why, actually, so to start with, this is the absolute value of the function x times x minus 2. So if I didn't have the absolute value there, I'd know it's just a parabola passing through those 2 points. So as a sort of scaffold, I'm going to draw this. This isn't my function, it's just a little piece of information that helps. Now I'm going to take the absolute value of this, so it is going to come down, taking the absolute value, bounces it back up here, goes off up that way, and some point 5 over here, 0 and 2. This sketch isn't necessary, but now that I'm looking at it, I have a good idea of where these critical points are. I suspect, I know there's a stationary point, and I know they're going to be, well, the derivative is not defined here. So that's very helpful information that I know what the answer should be. I do want to do it, well, let's just go through the list. So firstly, the endpoints of the interval are x equals 0, x equals 5. Okay, well the stationary points are where the derivative vanishes. So unfortunately for this function, to take the derivative, I do need to get these pieces correct.
Josh, would you have to write the y coordinates to get the points?
It's a good question actually. Personally, I don't think so. I think I'm just looking for the points in the interval,
Yeah,
which are the critical points.
I might be inclined to agree with you, but put them in anyway, just in case.
Yeah, well, I definitely want that information because the second part's asking me about the function values there.
Yeah.
So yeah, let's add that information. So, well, these are the endpoints of the interval. So. Just add the information that f of naught is, well, you plug that into the function, you get the absolute value of naught. The other endpoint was f equals 5 with f of 5. It's the absolute value of 25 minus 10, so the absolute value of 15. So, well, that is just 15. Okay. So those are the endpoints. Next, I want to find the stationary points. I think to do that, I'd better rewrite this function in a way I can easily take the derivative. So I'm just going to rewrite this as a piecewise function. So another way to write down this, and I can use this plot to help me, is to note that f of x is as a piecewise function. So if we were just over here with where it was positive, this would just be x minus 2, and this is for x less than or equal to 0, or x greater than or equal to 2. So either both these factors are negative, or both these factors are positive. And in the other case, when one of them's negative, so in this case, this one is negative, then you'll have minus that. That's x less than 2, greater than 1. So I can use this formula to work out what the value of the derivative is. Yeah. So using this, I can confidently state that the derivative of this is, well actually this is probably not the best way to write that, I'm taking derivatives. Now I need the product rule, so I'm going to go back using that. That was 2x minus 2. And this is actually only true away from the 0, so it's only true away from the 0, so strictly to that side of the 0, or strictly to this side of the 2. And the other one, well, if you take the derivative of this one, you'll find it's minus 2x plus 2. And that's strictly, where did that 1 come from? Alright, so I can look at this and try and work out where these vanish, try and work out where these have a derivative of 0. Okay. Well, actually both of these, regardless of where you're looking, this function here as a function of x only vanishes when x equals 1, which is in here. This also vanishes for x equals 1, but that's not relevant because this thing is never 1. So, yeah. So away from at least 0 and 2, we have formulas for the derivative. 0 and 2 themselves, I'll have to come in back and check. Anyway. So for using this, we see f prime of x equals 0 when x equals 1. So there's a stationary point at 1. And I'm just going to say that, remind ourselves that if we plug f of 1 in, so this is going to be this formula here, or we can get back to this, it might be a bit easier. It's 1 squared minus 2, that's minus 1. It's the absolute value of minus 1. It is equal to 1. And the last point I want to look at, well, I feel like I want to demonstrate that the derivative is not defined here, and the easiest way to do that, I think, is to just look at the limit of the left and right hand side here. Because I've already got 0 as a critical point, I'm not going to examine that point again. I'm just going to consider this point here too. So away from 0 and 2, I know it's differentiable. So away from 0 and 2, f prime of x is differentiable but, well, I look at the limit. Well, if I just look at the limit, say, of the derivative, as I approach x from below, so if I approach 2 from below, well, that will be the limit as x approaches 2 from below of this function, which is minus 2x plus 2, which is minus 2. This has become a minus 4 plus 2, which makes sense given the picture. And limit of this is the limit. So the limit as we approach from above, well, that's the same as the limit of 2x minus 2, which approaches 2. So it's not differentiable at x equals 2. So that's also a critical point. And I might just double check, remind what the value is. So the formula itself makes perfect sense at 2. You plug in 2, you get the absolute value of 0. Alright, so there was only 2 points where it was possibly not differentiable. That was 1 and 0 and 2. I already classified 0 as a critical point, so I found all the critical points. The 4 critical points, are 0 for 2 different reasons in some case, from my point of view. So 0 and 5, 2, and this one here at 1. Okay. So I guess if you're doing this question, you have to convince the examiner you know what the critical point types are, and that these are the ones we're looking for. So the next part, part 2, to find the absolute max and min. Well, there's a lovely theorem we can use. The lovely theorem is that if you have a continuous function on a closed interval, you know that the absolute maximum and the absolute minimum occur at a critical point. So this is why it's good to actually know the values at those points. So I would just say that since, well, this is a continuous function. I mean, you've just taken a continuous function, applied it to a continuous function. So since f is continuous over 1, 5, we know the absolute max or min occur at the critical points. And, well, the whole part of the first question is you find those critical points. So, namely, these are the following critical points. So we have our x, I'll write them as a table. So we know them, one of them was at 0, 1, 2, and 5. These were the only critical points that existed. The function was 0 there, 0 there. We plugged it in and it was, plug it in again, so it was 1 minus, yes, 1 there. And if I remember correctly, 15 here. So these are going to be the max and min, well, yeah, the max and min values are on this list. So I can just read off and see which is the smallest value on the list. The smallest value is 0, it occurs twice, and the largest value is 15. So hence, the absolute max is 15, and absolute min is 0. So that took a lot of writing. I guess I was trying to be very explicit about where the critical points were. So, criticisms?
I think that was, as a marker, I'd probably come at this and see what Josh has written and be absolutely confident he knows what the definition of critical point is like analysis of the fact that the limit doesn't exist at 2, flawless. But you've done all this work for what I would say is 1 mark. The part 1 of this is probably tops 1 mark worth of material. So awesome math, but I mean this is a 20-minute exam and you took 10 minutes to get 1 mark.
Yes.
So as a marker I give you 1 mark and say that's really good, but you left yourself no time for the rest of the test. And this happens all the time in final exams. Typically you see people doing the early questions and they put all this energy into only a quarter of the exam. They put like half the time into something that's only worth a quarter of the marks. Be very aware of that. If you find yourself doing something that takes a lot of time and it's one part of a 3-mark question, really cut it right down. As a marker, the question says find the critical point. So I'd be happy if Josh, if you just said 0, 1, 2, 5 diagram, and along with that definition, these are the critical points, and along with their y values.
Yes. So maybe a much shorter way to do is state what a critical point is. Mark would be very happy if you told them you understood what all critical points were. Maybe make this graph and then say, and based on this, these are them.
I mean, I can see that there's a turning point here based on just on the fact that you know where the turning points of a parabola are. And that there's a discontinuity here thanks to the absolute value function. Yeah, look, I think this would be a 3-mark question. 1 mark for knowing what the roots are, 1 mark for knowing what the max-min theorem is, and then 1 mark for just stating what the absolute max and min were.
Yes.
Cool. All right, next question. Sweet. Wasn't there some science fiction story where a guy's he's a maths genius and he tries to join the Navy and he has to do this kind of trivial, just numeracy test. And he spends all his time developing it. Like, the questions are trivial, but it's poorly worded, so he spends like the whole 2 hours developing this entirely new theory of fluid dynamics on the first question. There's 50 questions. He fails the exam, but publishes a paper on the on what he wrote. Anyway, my question: differentiate this. All right, easy. 3. I'll just say. Alright, now I always embarrass myself when I do things like this. You have to use the chain rule, but I forget where the coefficients go. So I like to introduce a variable just for my own sake, because otherwise things go bad. I'm going to let u equal 4x plus 1. Then this becomes x. Okay, no biggie. I need to take the derivative of this thing with respect to x, but it's a variable in u, so I have to use the chain rule. I have to take the derivative of this, not with respect to x, but with respect to u. So this is going to be okay, now I'm comfortable with what's going on. Du dx, well, that's just going to be 4. Du of this is 1 on. And now I need to eliminate the u's. The u is just introduced for my benefit, and I need to rephrase the answer back in terms of the original x, so this will be 1 plus. An easy question.
Yes.
Cool.
Right. So the only thing you really need to know for this question, well, chain rule, but you will need to know the derivative of tan inverse u. So, yeah, I think there are questions where they ask you to prove what this derivative is, but for this question you just should know it. You should know it is 1 over 1 plus u squared. So yeah, there's not really too much for this question. This was a 1-mark question, so they're really just testing maybe it's part memory, part understanding. All right, cool.
Easy question. All right. Maybe we will get through all this.
So I'm kind of in two minds about this question. So this next question is to find the limit of this function here. Now there's two things that immediately jump into my mind when trying to take this limit. So if I look at it, the top, for example, when we approach 1, the top goes to 3 minus 5 plus 2, the top goes to 0, the bottom goes to 0. I think, well, that's a perfect candidate for L'Hopital's rule. But for this particular one, I'm wondering if that's what I should really do. Because in this particular one, it might be easier to factor it. But then again, factoring a cubic is not too easy. So actually, I think I'm going to try L'Hopital's rule. Because I think I'm going to get that one right, where if I try to factor it, I think I might get it wrong. Right, so 3, the limit. We're looking for the limit as x approaches 1 of 3x cubed minus 5x squared plus x plus 1 on top of x squared minus 2x plus 1. And since this is of the form 0 over 0, I can try and get this as the limit by taking the derivative of the top and the bottom. So I'm going to say, if it exists, this should be the limit of 9x squared minus 10x plus 1 over 2x minus 2. And I have used a rule to get here. I'm trying to use L'Hopital's rule.
But you don't know that that's equal yet.
Yes, so
this is not.
This is one of the things about L'Hopital's rule. It says, well, as long as this exists, this should be the limit. Well, I'm never quite sure in a test how I would convince the examiner of that. So it's equal to this provided it exists. So maybe if I'm being more clear, I'm attempting to use. I mean, I'm allowed to explore. I'm allowed to see what happens when I do this.
But you also haven't. Did you write that it was 0 over 0? Or sorry, is it 0 over 0?
It is. So
How
that's
do you
the
know
first thing I checked. Well, I plugged in the numbers. All right. And if I explain my reasons, I think I'm allowed to do this. So it is of the form 0 over 0. That's an easy check to do. Do make sure you actually do that, just not state it. And I'm allowed to attempt to use L'Hopital's rule here. So I could go nowhere, but I'm pretty sure this will give me a good answer. Now, if I look at this one, well, the thing is, this thing doesn't actually, I can't evaluate this at 1. If I plug in 1, I'm going to get 9 minus 10 plus 1. That's 10 minus 10 is 0. On the bottom, you'll have 2 minus 2, also 0. So, yeah, I'd like to find the limit of this thing. So, well, yeah, I'm going to attempt to use the L'Hopital's rule again. So if I apply the derivative to the top, I get 18x minus 10 over 2. So, yeah. I'm trying to think. I guess maybe what would make some examiners happy is if I wrote this was equal to this, provided this limit exists. Because I'm never actually claiming it does exist at that point. And this, I'm claiming equal to this. And again, well, I'm attempting to use L'Hopital's rule since it is of the form 0 over 0. This, well, this is really a question mark about whether this exists, but this one does exist. This one is equal to 18 minus 10 over 2. It is 8 over 2. It is 4. So while the limit here is 4, and I guess I have to justify my use of L'Hopital's rule. So how would you write an answer to this question, I guess?
Okay, so L'Hopital's rule is, it's got conditions on it. You can't just say that this limit, the limit of this function is equal to the limit where the derivatives, you've taken the derivatives. Right? There's two things you need to do before you can make such bold claims. The first thing you need to do is realize what form this is. Is this something of the form 0 over 0? And I'd like to see, as a marker, I'd like to see some acknowledgement of these conditions. Yes, this is of the form 0 over 0. Simply writing this, that's okay. That's okay. I'm all right with that. But you demonstrated that you know one of the conditions of using L'Hopital's rule. The other condition is that you know they're only equal if this latter one exists. You can't just say they're equal because you don't know this exists yet. You only have equality when this exists. So I guess the question mark here is indicating to me that Josh knows about these, but please, when you are using L'Hopital's rule, be aware that it's not just something that guarantees that this limit is always this limit, equal to this. There are conditions. You have to have a function of the right form, a 0 over 0 or infinity over infinity, and this second limit has to exist.
So I guess if I was to write it more cleanly, I could say the given limit is of the form 0 over 0. So I guess what I might do is actually say that that is equal to this, but then actually add a condition to that.
I wouldn't even put the inequality in. I'd say I give these things names, f and g, and then say the this limit is equal, limit as x goes to 1 of f prime over g prime is this, and then because that's also over infinity, you have to take the limit as x goes to 1 of f double prime over g double prime, and then because this exists, then it's equal to this limit, and because this exists, it's equal to that limit.
Yeah.
Can I write that?
Well, yeah, I think.
What do you want to write it?
Well, essentially, I was going to iterate over this sentence. I was going to say, now that I've gotten to this point, provided it exists.
Yes, the equalities though. We need to do something equalities. Can I drive? I want to drive. Sure. Thank you. So the limit is of the form that. Okay. Good. So we'll say let f of x be equal to the numerator and g of x be equal to the denominator, 2. Right. Now, you can't say that these things are equal yet. You don't know that yet. What you can say is that the limit is x goes to 1 of f prime over of x, g prime over x is equal to this, where you take the derivatives, and this is also of the form. Or you could even just say this is equal to 0 over 0 if you like. Well, maybe that's not even, is of the form. Okay, good. Now you don't know this is equal to this, you don't know that yet. So that only happens when this is, you know this exists. This is equal to that, which is equal to, as Josh says, 4. Right. Now you're in a position to invoke the fruits of L'Hopital's rule. You know this limit exists. Therefore, by L'Hopital's rule, it's equal to this. Four is equal to 4, being this limit, is equal to this limit. That's what L'Hopital's rule tells you. And it's only now you can start making the conclusions of L'Hopital's rule. And say maybe twice, because we're really invoking it twice, which is lim which is the original limit. So by using L'Hopital's rule again, since this limit exists, you know it must be equal to this. Okay. So that's how I would have done it.
No, I like that. At no stage have I actually managed to. Well, at no stage has Daniel in this case managed to
prematurely
claim
conclude
equality between things which we're not sure yet.
Yeah. Only down here am I concluding that this is equal to this is equal to this.
Okay.
Only when L'Hopital's rule actually says it so. Right. Next question. Oh yeah, that's all. I think we're going to go more than an hour. Okay. State the mean value theorem, find a point C satisfying the mean value theorem for this particular function and this interval. Right. Please remember what the definition of the mean value theorem is. You, as a marker, it's kind of high. You need to do a lot to get the mark for this. You need to say the function is continuous. You need to say continuous on which interval and differentiable on which interval, and then the conclusion here. And if you have all 5 bits, then you know the definition of the mean value theorem. Right. Now, the mean value theorem doesn't actually tell you where C is, it just tells you it exists. So we actually have to do a bit more work here. We need to apply it to this function and actually find C. The mean value theorem won't give it to us, it'll just tell you that there is such an answer. We have to use our smarts to actually go find it. So when you're using the mean value theorem, this is enough. You have some function, just state that you know the premise of the mean value theorem before you start going towards its conclusion here. So you need to acknowledge that this is a function which satisfies the conditions of the mean value theorem, and then you may apply the conclusion of the mean value theorem. So then f prime of f prime of c. Let's just do what this is. F prime of c, which is say c squared 3c squared minus 4c, is equal to f of 2 minus f of 0 over 2 minus 0, which is equal to, well, f of 2, what is f of 2? 8 minus 8 plus 5. And f of 0 is 0 minus 0 plus 5 over 2, which is 0. Okay? So I need to find c. So 3c squared minus 4c is equal to 0. So I can say that c times 3c minus 4, which means that c is equal to either 0 or 4/3, and I might cross off the 0 because zero's not actually in my interval. This doesn't belong. The c that was promised by the mean value theorem is this one. This is the one that's in the open interval between 0 and 2. This one is not in the open interval. Josh.
Yeah, so I think that's actually intentional. They want you to realize that, well, although this point does give you a 0 derivative, it's not in the interval. It doesn't count. The theorem said, I promise you there will be a point inside the interval. Here you got, well, something around about 1.333, so forth. So this is the one. This is the one that's strictly between 0 and 2. This is the one that was promised by the theorem. So yes, that's actually, the theorem does explicitly have that in it. It does say in the open interval. But yes. So I guess you'll just have to remember this definition. If you get a question asking you to state the mean value theorem, you'll just need to state what it says.
Yeah, and remember which one is open and which one is closed.
Yes.
All right, next question.
Okay. So I tried to pick, when we're picking these questions, we tried to pick a nice wide range.
This one. Oh, yeah, okay.
I might
Yep.
just put it at the bottom.
Squeeze it in.
I'll bring it up if it's not visible. Actually, it looks like it's all visible. I might bring that question up a bit higher later, just so people know what's coming up. Okay, so this first question is asking us to just use the definition of the derivative to actually show that the derivative of this function here is what we expect. So we have a lot of tricks for actually just finding this without having to use the definition, but in this case they are saying let's do it once. Let's actually use the definition to find this. So question 1. So by the definition, of the derivative. So here I'm just going to state what the definition says. The definition says that the derivative of a function at the value x should be equal to a limit as h, some number h approaches 0, f of x plus h minus f of x over h. It should be equal to this limit. So we're going to have to calculate this limit. And the only way to do that is actually to put in the formula we're given. So let's plug this formula into this definition and see what happens. So this is going to be minus 2x plus h squared plus x plus, where did my limit go? So this limit is the limit as h approaches 0 of this minus, let's put some brackets so I don't make mistakes, minus 2x squared plus x all divided by h. Now I need to do a little bit of work to simplify this. So it's a little bit of algebraic simplification. Alright, so, well, this is not too hard to expand. Just binomial theorem tells me it's minus twice x plus 2hx plus h squared. The other plus x plus h, that will be minus, I'll just get rid of this bracket here actually, plus 2x squared minus x, all of that divided by h. Well, there are a lot of terms here that cancel out, which is what we would hope for. I know that this term cancels out this term. If I do look at it, this is a minus 2x squared. So there is a minus 2x squared, and that cancels out with the 2x squared. So that term and that term will cancel out. And what you end up with is the limit as h approaches 0. And let's just explain the entire top. You get minus 4x, minus 4x hx. I don't know why I changed the order. So minus 4hx minus twice h squared. There's a plus h all over h. And, well, that has a factor of h. H is not 0. We're always away from 0 when taking this limit. So we're never actually equal to 0, I should say. So if you cancel out a factor of h from everything, this becomes minus 4x minus 2h plus 1. And, well, as I take the limit, this is just a number. This just is a number minus 4x. This is just a number 1. And this term goes to 0. This term vanishes. So that limit I can easily take. It is just minus 4x plus 1. So it's a little bit of algebra. It seems like quite a lot of algebraic work, so I'm trying to be very explicit. But I did end up finding the limit. The limit is just what we were told.
This is exactly what I would hope to see if someone was asked to do this. This is perfect. Nice definition of the derivative, application, things cancel. It's perfect. Next question. Okay. So, my question is to find the tangent line to this strange beast of a function at the point 1, 1. Okay, so I've got the point where it goes through. All I need to know is what is the derivative of this function. So I need to find dy dx. I'm just going to boldly differentiate this thing and see what happens. I kind of know what happens when... I'm confident this is going to work out, and I'll explain why. So d dx of x plus L. So the thing you shouldn't attempt to do with this question is to express y as a function of x. Do not. This is not going to get you anywhere. I'm going to take the derivative of this thing with respect to x, and I know I'm going to pick up the dy dx along the way. This one here is easy. This is just 1 plus 1 on x. This one, I can't differentiate this with respect to x. I can only do it with respect to y, so I use the chain rule. So, and this is okay, dy dx times this thing, which is 1 plus 2 on y. Okay. It's not so bad. I've got my dy dx here, which I don't know, and then I've got a relation with dy dx. Maybe I'll just write it out. 1 plus 1 on x. And I could even bring that over there. 1 plus 2 on y is equal to dy dx. Okay, my dy dx in terms of x's and y's. But all I really want to do is evaluate this at the point 1, 1. At 1, 1, dy dx is equal to 2 plus 2 over 3. 2 over 3. Awesome. Y minus 1 is 2/3. X minus 1.
Yep, so I mean that's exactly what I would do. I know I have no hope of actually solving this equation in terms of y. I don't think anyone really does have a hope of solving that.
But maybe people who are used to first taking y as a function of x and then finding the derivative might attempt to do this. Do not attempt to do that.
So yes, this is I believe called implicit differentiation. So it's really nice. Your answer does depend on y, but we were told the point was 1, 1. So we had an x and a y value to work with. And yep, you find your slope, and you hopefully know the equation for a tangent line. Yep, so that's all there is to it.
Next question.
Alright, so this next question, it's not a short question, this is a 3-mark question in previous tests. So you want to find how many real numbers satisfy this cubic equation here, And it does say you must give reasons and naming any theorems we use. There was a further line I didn't write because it's a little bit long. It is, your hint is to actually find the stationary points of this polynomial. So we should probably start with what hint they gave us. Let's actually start by finding those stationary points. Okay. So the cubic. So what is the cubic? So if I'm just looking at this as a graph, this cubic has stationary points when f prime of x. So we know how to take the derivative of a polynomial. It is 3x squared minus 12x, and it's when that is equal to 0. Well, this one's not too hard because that is 3x times x minus 4 equals to 0. So x equals 0 or 4. So these are the stationary points. So that's helpful information because I have a cubic, I know its stationary points. Now, if I knew what the value of these, if I knew what the function value of the stationary points were, I'd have a much better idea of what's going on. Let's just check at x equals 0. Well, what I called f of 0 is just 1. At x equals 4, look at the function value, it's 4. Alright, so this becomes 4 times 4 times 4, that's 64. 6 times 16 is, where's number 4? So
It's 30
times 16, 60 plus 36, so it's 96. So 64, well actually 65 minus 96. If you go through the calculation, you find it's minus 31. So maybe I should do it a bit slower, but yeah, that is the correct number. So just our experience with cubics tells us we know what's going on, but I think they would like you to do a little bit more of a formal argument using the theorems that we know. So let me just roughly sketch what I know is going on. I know cubics tend to look like this, especially because it has the x cubed term there. I know that this point is actually at 0, 1, so that's actually not a very good drawing because it did actually, the axis passed through here. And I know this is a negative.
Let's draw it again.
Yeah. Yeah. So I should not add the axes first. So I know it looks like this. I know there are 2 stationary points. I know that the first one actually occurs when x equals 0, and it's slightly above the y-axis. This other one's actually fairly far below the x-axis. So roughly speaking, it looks like that. So I know what should happen. I know I'm going to be able to find one over here, sort of one in this somewhere. Wait, I know I'm going to find one somewhere between 0 and 4, and there should be one after 4 and one before 0.
Can I draw this again, but a bit bigger?
Okay.
Bigger. But essentially it's exactly what you said, but I just want it bigger because we're going to do some work with this.
Yeah.
So here, like slightly above that, and then, yeah. Cool.
Okay, so at this point I know to be 0, 1. This point I know to be 4, minus 31. Actually, this formula does tell me a little bit more. It does tell me what the value of how the derivative behaves on these intervals. So
let's start here and just prove that there's a 0 in this interval. That's
Okay.
probably the first thing to do.
okay. Right. Okay, so if I want to prove there's a 0 there, the tool I would like to use for that is the intermediate value theorem. Now, the intermediate value theorem has a few conditions we need to state. First condition is it must be, the function you have must be continuous. It must be, so you have a closed interval, you have a continuous function on that closed interval. And you also have to have the fact that it changes sign. I know it changes sign from this. And I'd just like to remind the examiner that I know what the conditions are. So since f of x is continuous on the interval, so the interval I'm caring about is 0 up to 4, and so we have a continuous function. I know that f of 0 is less than 0. Oops, no, it's not. I know that one of these values is greater than 0 at one endpoint, and the value at the other endpoint is less than 0. So continuous function, this interval, and a change sign. So the intermediate value theorem says there is a, well, there is a value c in 0, 4 such that f of c equals 0. So this value was intermediate between these two, so it means I'm able to find. I'm promised that there is one. I might not be able to tell you exactly what it is, but I know there's one there.
Can we call it C1?
Sure.
Let us name it C1.
So this is the first one we
Good.
found,
And
C1.
Excellent.
Okay, so we know there's one here. I would like to prove beyond a doubt that there's definitely one here. So I have a positive value here. I start slightly above the x-axis. I'd like a value which puts me slightly below the x-axis. So I could try just putting larger and larger numbers in here, but if I notice actually if I just put in x equals -1, this is a, well, this is -1, cancels out that one completely, and we just get a -6 left over. So I don't need to search too far. If I just put in, if I just look at f of -1, it works. Right. So note f of -1. So you really just need to find a value which does what you want. Is equal to -6. And, well, let's just state it again. Since f is continuous on the interval -1 up to 0, and now we found that we went from a negative number to a positive number, the intermediate value theorem says there is a C, well, the second one we found, strictly, well, strictly inside? No, it is. There's a C somewhere in -1 to 0, such that f of C2 equals 0. So if I look at -1, there's another value here, C2. So the intermediate value theorem says there's definitely a root in here. So again, we use the fact that it's a continuous function and a change sign. So I just need to find one more point here. So I need to find some point where it changes sign again. If you look at this, well, the first one that jumped into my mind is I can actually perfectly balance these two terms out if I put in x equals 6. If I put in x equals 6, that cancels with that and leaves me just +1 left over. So it turns out if I just look at 6, you will find that it actually does pass through the point 6, 1. So this point is not, you can choose other numbers. You'll probably end up choosing a number bigger than 6, but 6 is the first one I found just looking at it. I have a, oh. So I'm just going to state again, so since f is continuous on, well, in this case I'm looking from 4 to 6, so the interval I care about is 4 to 6, and well, we had that f of 4, that's actually minus 31 less than 0, and f of 6 was greater than 0. We have, by the intermediate value theorem, a C3 inside 4, 6, such that f of C3 equals 0. So there's another number here, C3. I can't tell you much about them at the moment, except for it's between minus 1, 0, 0, 4, 4, and 6. And I guess there's one thing. Would I use the fact it's a cubic to just say that these are the only ones?
You could. I don't think that it would be part of the question. Take for granted that the cubic has at most three roots. I think the real purpose of the question is creating these closed intervals the way you have here. I mean, this one's kind of given to you, and then this one you need to work a little bit to get the -1, and you have to work a little bit to get the 6. And you know it's the IVT that gives you this, and you notice that f is continuous. The one thing I would do is to maybe just add a little bit here. So this is -31, and just to demonstrate that you have actually calculated what these things are. Some people just say f of 1 million, and that's greater than 0. Well, no. You have to be a little bit careful about choosing these things. You don't just choose some crazy big number and hope that it's greater than 0. But look, you've done it on the diagram, so that would be fine.
Yeah, I mean, I don't mind if you use f of 1 million, but in that case, I do expect you to tell me what
f of 1 million is. Yeah.
Yes, it probably works. In fact, I know it works in this case. I don't know what it is. Okay.
Next one.
Next one.
All right, we'll get there. Oh, thank you. I have a nice limit question, and this is going to be a L'Hopital's question. Now remember, L'Hopital's rule doesn't tell you exactly what this limit is straight up. There's conditions before you can actually start invoking the conclusion of L'Hopital's rule. If you start just saying that this limit is equal to something else, that's like going to the shops and just walking out with the stuff before you've paid anything. You haven't done what you need to do before you can start getting the conclusion from this. First, demonstrate that that what you have actually satisfies the assumptions of L'Hopital's rule before you start rolling with the conclusion. So, the objective, find okay. Two things. First, it needs to be of the form going to 0 over 0 or infinity over infinity. Well, as x goes to 0, tan of x goes to 0, and as x goes to 0, x goes to 0, it's of the form 0 over 0. So we're halfway there. Let f of x be equal to tan of x and g of x. Since this is the other condition. The existence of this limit is the other condition. This is sec squared 1, and as x goes to 0, sec squared is just 1 and cos squared, so that's just 1. Aha! Aha! This other limit exists! Excellent. You're in a position to conclude the thing that L'Hopital's rule tells you to conclude. To continue the analogy, we've paid for the stuff and now it's time to walk out of the shop. By the conclusion, by L'Hopital's rule, the original limit is equal to whatever that was, 1.
Very nice. So in terms of that analogy, when I did this question before, I walked out of the shop and said, no, I'll pay for it later. I definitely will. But no, it's good to pay up front and then...
I wasn't going to let you walk out of the shop without paying first.
Okay.
I've seen it too many times. All right, let's go. Next one. Last one. All right.
Right, so this very last question is you're given this piecewise function here, so that's visible, yes. So you're given this piecewise function, so before 0 it's defined in terms of this a times an exponential plus b, and after and including 0 it's actually just defined to be the sine of x. And now you want to find all real numbers a and b such that this thing now becomes a differentiable function. Well, an important thing about a differentiable function is if a function is differentiable at a point, it has to be continuous there. So the first thing I should do is actually make sure this function, find what I need to make sure this function is continuous. If f is differentiable at x equals 0, then it must also be continuous. Well then, maybe I won't say it must also, I say it needs to be continuous. That's what we need. We need, well, what we need is that the limit as x approaches from below f of x to be equal to limit as x approaches from above f of x must also equal 0. Now, we can look at each of these individually. Turns out 2 of these are exactly the same. So the limit as x approaches from below. Well, I know what the function is defined to be in that case. It's this exponential combination. So it's the limit as x approaches from below a e to the x plus b. And well, this is a continuous function. I know what its limit is at 0. So, and if I'm approaching from one side, it's the same. So this is just going to be a e to the 0 plus b. It's going to be a plus b. And the limit as x approaches from above f of x is the limit as x approaches 0 from above of just sine x. Well, we know this. This is just the sine of 0. The sine of 0 is 0. That's right, that's sine of 0 equal to 0. And actually that's also what happens if you just plug it into the definition. So this definition said if you just plug that 0 in, you just get the sine of 0. Right. So the condition is we must have a plus b equal to 0. I might just put a box around this. So this is the first thing we need to know. Right, now, I have seen this question in tests before. A lot of markers I know tend to want you to do this next part using the limit definition of the derivative. They want to make sure that the limit definition works. Although when you do that, you do need to have two tools to apply that. So based on the advice I've been given by somebody else, I'm actually going to remind ourselves of two tools we have. So the bare minimum I need is that since e to the x is differentiable at x equals 0 with derivative e to the actually no, I don't know how I wanted to state that. So I'm going to actually restate how we get that fact. So I'm just going to take this as something we know. We know that d dx of e to the x equals e to the x for all x. And what that really implies, well, that implies that if you were to take the limit as x goes to, as you take the limit as h goes to 0, e to the x plus h minus e to the x over h is just e to the x. So if they want, there's only one way I've been able to see to actually use the formal definition, and that's to start with some facts that we know. So we know that the exponential has that derivative. That means as a limit, it has this. Similarly, you know the same thing's true for sine. We know that the limit as h approaches 0 of the sine of x plus h minus sine of x over h is just the same thing as the cosine of x. And that's true for all x. So I do need these two tools if I'm going to do this using the limit definition. Alright, so first thing we needed was continuity. That gave me a plus b equals 0. The next thing I need is I need to make sure that the limit as h approaches 0 of f of x plus h minus f of x over h actually exists. Which means the left and right hand limits must be equal. So I might just rub that out. So continuity was something we needed. It gave us one condition. But now for differentiability, we need the limit as we approach, what we need is that the limit as x approaches, differentiability, we need that the limit as h approaches 0 from below f of x plus h minus f of x over h to equal the limit as h approaches 0 from above f of x plus h minus f of x over h, which is a fancy way of saying I need the limit as h approaches 0 to exist. So the two left and right hand limits must be equal. Well, I did say that a little bit too generally. For differentiability, the question's actually not asking everywhere. The question just asks us to do it as x equals 0. So I need that 0 plus h minus f of 0. I only really care about the point 0. So for differentiability, we need that. I can look at the left-hand limit. So the left-hand limit is limit as h approaches 0 from below. So if I'm just looking at f of h, where h is a negative number, I apply that and get that this is just a e to the h. I probably should use this fact now. So this fact can be used to tell me that b is equal to minus a. So it's a e to the h minus a. And I'm going to subtract off f of 0. Now, here's where I think this is why people sometimes like you to do the limit form, is that f of 0, as I said before, is the sine of 0. But the sine of 0 is equal to 0. That's just 0. And then, so I need the left-hand limit is this. And if you, well, that's the only way I can really evaluate this limit is to recognize that this is actually the definition for the derivative of e to the x at x equals 0. So this is a e to the 0 using, well, I'm kind of using this fact here, using fact 1 I stated with x equals 0. So I need to know that if someone was giving me this, so in this case with x equals 0, I know it is just equal to that. The other thing you do is you now take the right-hand limit. Is, well, the right-hand limit is the limit as h approaches 0 from above, and maybe I'll write this a little bit more clearly, f of h minus f of 0 over h equals the limit as h approaches 0 from above, the sine of h minus the sine of 0 over h. And well, this is by definition the derivative of cosine at x equals 0. Sorry, this is the derivative of sine at x equals 0, which I know to be the cosine by 2 at x equals 0. Cosine of 0 is an easy number, it's 1. So what I need is that this a is equal to 1. So we need a equals 1, hence b equals minus 1. So those are the values you were looking for. Nope, I never actually numbered this here. Move this back. So this is one way to do it. Unfortunately, it does come down to, when you get to an equation like this, you have to just recognize by definition this is a derivative of sine at h equals 0, at x equals 0. So, what do you think?
That's crazy. I would never do it this way.
Although I remember last year we had issues with people people wanted their students to look at limits.
Yes.
For this one.
Yes. I maintain those people were wrong, and that the right way to go about it was the way that you and I told them to the first time.
Right.
So I might just do that now, because this is I would This is what, a 2-mark, 3-mark question?
It's a 3-mark question.
This is hard.
Mm.
For 3 marks, I wouldn't do it this way. Alright.
Right.
So let me show you how I do this question, and how I think
Yes.
how Josh would do it as well if given a free hand to do it the way he wants to. Am I right?
Yes. So there is another fact which makes this a lot easier. So I did run this sort of question by our director of first year. He seemed to think that using limits was not beyond the 1141 students, doing that in terms of limits. So
Okay, yeah, look, that's true. The 1141 students would be able to do that. Okay. I'm just going to write up a theorem real quick. So this is okay. So this is the. I'm sorry to copy that verbatim, but this has caused trouble in the past. This is a theorem from your book. For a fixed number, let's call it a, and function piecewise defined function like this, where the function is some continuous and differentiable function p on the right of a, and some other continuous and differentiable function q on the left of the point a. Then if f is continuous at the point a and f prime at a is equal to q prime at a, then the function is differentiable at a. What this is actually saying is, if the function is continuous at a, that means the two kind of halves meet, and their slopes are equal, then the function is continuous, is differentiable at a. And that's essentially what Josh did, but it's neatly and compactly brought to you, packaged for you in the form of this theorem. So let's just go ahead and do this. F is continuous at a. Well, f is continuous at a. At say at x equals 0, if, well, let's see, what is this as x goes to 0? If lim x 0 for below f of x equals f of 0. And what this is, f is, so with our definition of f over here, as x goes to 0 from below, this becomes a plus b. So a plus b, and this one over here, the limit as x goes to 0 from above is sine of 0, which is 0. So this is going to make our function f continuous. And the second half of this is to say that the derivatives match. So, and if p prime at 0 is equal to, let's see, p prime at 0 is just going to be a is equal to cos, then no, that's 1, sorry, 1. Then the function is differentiable. So a equals 1 and b equals -1. Makes I suppose the problem with this is that we need to show that this is the only way to make the function differentiable, that there are no other values. So is there something we could say to conclude that, well, okay, so this means we need it to be continuous, so a has to always be equal to -v, but is there some other way we could make this function differentiable?
So is that an if and only if statement? Is that
In the theorem, no. Well, the way it actually is, but the way it's stated in the book is not like that.
Mm-hmm.
So we need to do something to state that this is the only solution.
Continuities are given.
So but is this the only solution? Because the question is to determine all real values that make it so. Well, if it is we'll have to like it is, but how do we say that? That's the problem. Right. We need something more.
Yes. So I guess one advantage of working with limits is that you can, well, as long as you bring up those facts, you can say what the limit is from one side and the other side. You do need to borrow some advance. You need to borrow knowledge about what you've written down. In one case, you are writing actually just a formal definition for the derivative of the exponential. On the other side, you're just writing down the formal definition for the derivative of the sine function, and those you know.
Yeah, so just looking at the example in the book, they just in which we did previously was say it's by the definition of differentiability this, and then you have kind of equivalent conditions. So that's good. All right, we'll have to leave it at that, I think. Put something in the comments if you have an answer to this question. I'll try and put something in the comments and come up with an answer to this question myself. Look, my feeling is this is the way you're supposed to do this question, and
yes.
that the really this should be an if and only if theorem. I'll have to think on this. All
Right. Well, thank you for your attention, and I guess good luck on your test next week. Don't forget to post questions on the Moodle forum over the weekend if you like. I tend to always try to answer questions there. I like to try and give people help if they ask.
Yeah.
But you have to ask sensible questions.
Yeah, maybe a question like this would be a good question for the Moodle forums.
Yes.
All right.
So I'll think on this as well, see if I can give an answer.
Cool. You can ask a question and answer it. All
Okay.
right. Good luck, and we'll see you for the next stream.